Hello everyone. So in this video I'm going to talk about how we are going to do a sketch of a phase plot that would be part of a Bode plot, all right, for a bandpass filter. Just to refresh your memory, a bandpass filter is a filter that has a frequency response uh, that is like this, right? It has a low cutoff frequency and a high cutoff frequency and a pass band in the middle. Typically, we're going to use Sallen-Key topologies to create this filter. And so what we can do is we can cascade a high-pass filter with a low-pass filter. So the input goes into one end, and the output comes out of the other end of the second stage filter. All right, so that's how we can make a bandpass filter. All right, so again, to refresh your memory on Sallen-Key topology, so high-pass filters structures are like this. Low-pass filter structures are like this. And this is the transfer equation for each. So this one is a second order H of S, if you like, for a second order high-pass filter. This here is the transfer function for another second order, but for a low-pass filter. And this is for the first order low-pass filter. All right. So the problem we're trying to solve in this question is to create a bandpass filter that has the following specification: a fourth order high-pass filter with break frequency at 300 hertz, and a third order low-pass filter at a break frequency of 5 kilohertz. So that means it's 300 hertz here and 5 kilohertz there. But the slope will be different. On one side, that's on the high-pass filter side, that's this side here. The slope is going to be 4 times positive 20, so that's 80 dB per decade, positive 80 dB per decade. And then on the low-pass side, this is the low-pass side, yeah, this is the low-pass side, is going to be 3 times negative 20 dB. So that's negative 60 dB on this side. So positive 80 dB on this side, and negative 60 dB on this side. All right. So before we plot, we need to get some idea of how big this plot needs to be. So the first thing is we're going to try and figure out the phase degree range. So to do this, first thing you do is you just go and figure out how many S terms, lone S terms, yeah? How many lone S terms of zeros are there in the final transfer equation? All right, so since we need a fourth order HP filter and a third order LP filter, so that means for the HP filter side, we need to cascade 2 of these to get our fourth order. And then on the low pass side, we just need to cascade it exactly like this. That means we cascade a first order with a second order low pass filter. So this will give us a third order low pass filter. So 2 of these for fourth order high pass, and exactly these 2 for third order low pass. All right, so just bear that in your mind, because we need to figure out what is the order of S terms that are lone S terms of zeros. Well, there are no zeros on the low pass filter side, but there are zeros on the high pass filter side. In fact, there are 4 of them because each second stage is an S squared term. So if you cascade 2 of these, we'll get S to the power 4. So the answer is 4. So the maximum highest phase angle is going to be 4 times 90, so which is going to be 360. And the lowest phase angle, that's the range down here, we can work it out by just simply using this formula. We just go and figure out how many zeros there are in the entire system minus the number of poles in the entire system, and then multiply by 90. So how many zeros are there? Well, the zeros are only in the high pass filter, so not for the low pass. There's only 4. So there are 4 zeros in total in the entire system, right? And how many poles are there? Well, for the high pass filter, there are 4 because there's an S squared term down here. So if you cascade 2 of them, there'll be S squared, times S squared. So that's S to the power 4. So 4 poles for high pass, and then for low pass another 3, because we have the first order here and we have the second order here, so together becomes there'll be 3 poles. So 4 poles here and plus 3 poles there, so there are 7 poles and 4 zeros. So 4 minus 7 times 90, which means negative 3 times 90, so you get to negative 270 degrees. So 360 here, negative 270 here. I think I got my range okay, so that's done. Next, to figure out what is the highest frequency range and the lowest frequency range. For the highest frequency range, what you do is you look for 1 decade more than the highest cutoff frequency. The highest cutoff frequency is 5 kilohertz, so 1 decade more, that's 50 kilohertz. Next, for the lowest frequency, we look at the lowest cutoff frequency, which in this case is 300 hertz. So we look for 1 decade less than that, so that makes it 30 hertz. So we have 50 kilohertz, 30 hertz. So 30 hertz is around there, is there, and 50 kilohertz that's 10 kilohertz, 20, 30, 40, 50. So it's here. So we are inside the range. So we can use this semi-log graph sheet, if you like. All right. Okay. So next we're going to start plotting. So the way we do it is we plot for the different frequencies or different cutoff frequencies that exist that needs to exist in our system. All right, and also whether they're zeros or poles. So have a look. Looking at zeros first, we have a 4th order high pass filter. So the zeros will determine because it's a lone S term. All right, the order is just basically the order times 90. So here the order is 4, so 4 times 90, that means it's 360. So we're gonna have a at 300. All right. Anyway, so we're gonna have because it's a constant term, so you just have a constant term from 360 onwards all the way till the end. All right, till infinity. All right, so here I'm gonna put a line there. All right, so that's gonna be our zeros, a 4th order 0 at 360 degrees. All right, so that's done for zeros because it's just a lone S term. Now for poles, we have for 2 different frequencies. We have one at 300 hertz. There are 4 S terms. That means S plus something. In other words, this term here we need to factorize into something times something. S plus something times S plus something, and then we do it 2 more times. So once we have it in that form, then we will have 4 S terms, if you like, at 300 hertz. That's our high pass frequency. So the way we do this is we first mark the frequency of 300 hertz. So I'm gonna put a mark here at 300. So that's 100, 200, 300. So this is 300. This is 300. All right. All right. So that's 300. Okay. So that's 300. Okay. So then what we do is we then mark a decade less and a decade more than that cutoff frequency. So so this is 300, so therefore 1 decade more is going to be 3,000. So 1,000, 2,000, 3,000, that's over here. All right, and then 1 decade less than 300, which makes it 30. So we put a marker here. 30, 30. All right, that's 30. All right. All right. Okay, so now we have the frequencies marked. So the way we put our marker for the 300 hertz cutoff frequency is, well, we need to work out what is the order at that frequency. Well, it's a 4th order. So the frequency we're looking at for poles will be the order times -45. So we're talking about 4 times -45. That makes it -180. So we put a marker at -180 on the 300 line mark. So -180 is over here. All right, so that's on the 300 mark. Not quite there. Okay, I think it's there. Right. Okay, so that's at the 300 mark. And then we need to then mark a decade before that. So it should be here. So at 0, so that we have a 180 degree slope. All right, and also a decade later. So 180 plus 180 would be 360. All right, so there. So you have this shape here. So so then what we do is we then sketch for this part. So I'm gonna just replicate this. All right. Use a different color. Maybe I'll use this. All right. So hang on. Doesn't quite look center. All right. All right, and then it just goes down. All right, so it goes down all the way to here. And then it tapers off. So it stays constant till the end. All right, so that's our pole at 300 hertz for the high pass filter side. Next, we're going to do the 5 kilohertz. So again, we just go ahead and mark where 5 kilohertz is. So 5 kilohertz would be, that's 1, 2, 3, 4, 5. Well, that's very close. Okay, 1, that's 1,000. 1, 2, 3, 4, 5. So it's over here. I'll use a different color for this. Okay, let's say this color here. Okay, it doesn't look very. Make it a little bit bigger, thicker. All right, so okay, so then as before, we then mark a decade before that and a decade after that. So this is 5 kilohertz. So a decade before that would make it 500 hertz. So 1, 2, 3, 4, 5. That's over here. All right, and a decade more. A decade after that. So 5 kilohertz becomes 50 kilohertz. 1, 2, 3, 4, 5 here. All right. All right. So now we have the 5 kilohertz frequency marked. Now this is a third order. It's a third order form. So therefore, the angle would be 3 times -45, which is -135. So we put a mark there. So let's put a mark there. So we use a different color here. Okay, I'm going to use yellow. All right, so at the 5 kilohertz mark, I need to mark 135. Well, 135 is actually, oh sorry, -135, which is going to be the middle point between -90 and -180. So that's that. And then you do the same this time for 0 on the decade before that. And 135 plus 135, that's 270. So 270 is over here. All right, so that's 270. Okay, done. So then again, you sketch the the line to go from the beginning until here. So it starts at 0 and it goes around until here. Let me change the color to this color. All right, and then the slope comes down. So the slope comes down to here. And then finally it tapers off to a constant angle. So that's negative 27. All right, so now we have all three plotted in. Okay, so we have the zeros at s to the power 4, a lone s to the power s term, right? Okay, and then you have the poles, which are down here. Okay, so now we plot the resultant phase plot that will represent the system as a whole. All right, so what we do is we just simply add the various angles together. So this is 360. 360 plus 0 is 360. So it's going to stay at 360 all the way to here. So I'm going to put a line there. Okay, so I'm going to use a different color for this. I think I'll use black. Oh, or dark blue. Oh, I think that's gone under. Control down. Control down, control down. Ah, yes. There you go. All right, control down. All right, so that's the resultant. All right, so then from here onwards, so this is still 0. The blue one, well, this oh, maybe I should change this color to some other one. Let's say black. All right, so I say black. All right, so from here, from 30 hertz, there is a flat 0 degree per decade line there, and so is this. It's also 0 degree per decade, but this one is a 180 degree per decade line. So basically 0 degrees plus 0 degrees plus negative 180 becomes negative 180. So you then add a plot over here so that it'll end up at, by a negative 180 per decade down here. So all right. Okay, so that's negative 180 coming down. All right, so then there's another break frequency here. That means between 300 to 500 hertz, there is a difference. Well, is there a difference? Let me see. Well, actually, there's no difference. So in fact, this line will continue because at the in this range it's 0 degree per decade, 0 degree per decade. This is still 180, so that means it will continue on. That 180 will just continue on. All right, until it reaches this frequency. All right. Okay, now from here onwards, that means from this break to this break, there are, well, this one is 0, so that's not a problem. This one is a negative 135 degrees, and this one is a negative 180 degrees. So basically, if you add them, right? So negative 135 plus negative 180, you're going to get 315. So you get 315. So that's the That's the angle that you need to create. Okay, so 315. Well, what I'm going to do is 315 is kind of difficult for me to figure out where this is. So basically 315 is between 270 and 360. So it's going to start something like that, you know, somewhere there, and then it ends a decade later at 0. All right, so it ends a decade later at 0. So that's going to be negative 315. So this now becomes the continuation from that point earlier, and it will end here. It will end here. That's the next breakpoint. All right. And then from here to here, that means from 3K, 3 kilohertz to 5 kilohertz. Now this is 0, this is 0, this is the only one that is left, and it is at negative 135. So therefore, you're going to have a little kink there. Let me just take that aside. Okay, so basically this goes here, and this goes there. All right. So there's a kink there. So there's like this, come down, up a bit. And then from here to here, the only component left is just the poles. This is the 5 kilohertz pole. So it's just as to power 3 term. So then it'll just, actually this line just continues down. All right, it just continues down all the way to here, to negative 270. All right, and then again it tapers off. So it tapers off until it reaches negative 270. It tends to negative 270 until infinity. All right. All right. So that's basically, this black line is the sketch of our phase plot for a bandpass filter of this specification. All right. I hope you guys got that, and can pretty much solve for other cases. All right. See you next time.